This is FE Peer Review, the Flat Earth Peer Review channel. The date is July 29th, 2020. The video in review is titled Mountain Observations. The video is by Sky Free. I'm going to try to keep this short and concise, not my forte. I tend to ramble. The video we're looking at is a channel that I only just noticed today. Seems to have been around for about a year, seems to have a number of videos on long distance observations. I'm going to start just by quickly reading the comments I left on this video, and then we'll dive into the video and look at a few key spots. I'm doing this kind of in preparation for a longer little set of videos that I'm working on that are about long distance observations in general terms. And this kind of brought some of those points to mind. So here we go. Something to keep in mind: the closer you put the camera to the water, the more you're going to accentuate refraction, mirages, and similar effects. The more these distortions are introduced into the image, the worse the image becomes for yielding information on possible Earth curvature, because the view of the physical geometry is more distorted. So if your goal is to study atmospheric distortion effects, then putting the camera close to the water is useful. But if your goal is to gather accurate data about Earth's shape, then you want to minimize atmospheric distortion by taking observations higher above the ground surface. It's important to decide what kind of data you're seeking, then plan your observations around that. If you want to know what you look like, you don't use a distorted funhouse mirror. On the other hand, if you want to study how curved mirrors distort images, then the funhouse mirror is just the thing. If exploring the shape of the Earth is your goal, then another disadvantage of putting the camera close to the water surface is that waves and swells become more and more of a problem. Even on a calm lake, I would expect problems with that if my camera was just inches from the water. When observing over the ocean, I'd recommend getting at least 6 feet up, just for the sake of clearing waves and swells, which can be deceptively larger than they appear from a distance. Ideally, if the location allows, I'd do an ocean observation from the beach at about 6 to 10 feet above the water. Then I'd find a higher bluff nearby, someplace 35 feet or more, and repeat the observation. Having 2 sets of observations like that would help to identify any atmospheric or wave issues that might have caused distortions. So the video starts with just some random images that they must have collected over the last year. There's one here showing a large tanker off near the horizon. Cut the volume. And then they've got a little model boat on a lake, and they're somehow comparing these side by side as if there's something to be learned from that. I don't think there is. This must be from an earlier video of theirs. I'm going to take a look later on. So they've got these 4 images showing these 4 videos, these four boats. I don't know. I'll get to that. Anyway, it just starts with these random images, and then it moves ahead, and we see this lake in Colorado, and I'm going to turn the volume back on.
Hey everybody, welcome back. We've been in the process of moving from the Midwest to Colorado, and we found an amazing reservoir that's going to be perfect for future experiments and observations. This reservoir spans over a mile, so we're excited to make some longer distance observations.
Okay, a quick point here. If your goal in making these observations is anything to do with the Earth's shape, 1 mile is not going to yield any practical data, especially not by simple visual observations. If you're using some kind of super high accuracy measuring equipment, then over a mile you could certainly gather useful information. You know, if you're using high-powered land surveying equipment. But with a camera in your eyes, you're not really going to get anything useful over a mile. Let's see if I can remember. The dip over a 1 mile distance is going to be about 8 inches. And if you look at the bulge between the 2 points, you're talking about 2 inches. Measuring 2 inches over the course of a mile, or seeing 2 inches over the course of a mile, is not really within the realm of reason.
We didn't have our boat with us out on this first day, but we did focus on some pelicans out on the water. For reference, the pelican's head is about a foot above the water, while its body, which could represent the hull of a ship, is about half a foot above water.
I really don't think that a pelican's head and body are going to serve as a useful substitute for a tanker ship on the ocean. You're not going to get useful data from that. We'll see what you come up with in future videos, but I'm discouraging you from spending too much time pursuing that avenue. These things don't just scale up or down. It's not like a model airplane that you build in your when you're a kid. You know, these things don't scale. There's more to it than that. They then pull up the Walter Bisneln Earth calculator, which includes refraction, and I was pleased to see that they actually used that to check some numbers. However, they've got refraction at 0, a, practically a physical impossibility. There's virtually always atmospheric refraction happening, and the number here would be positive. On a few rare occasions, you get a kind of reverse effect, and that would result in theory, a negative refraction index. So clearly, when you're passing from one of those rare occasions back to the normal occasion, you're going to pass through 0, but that's not a condition that you're likely ever to catch on camera.
At 0.6 miles, there should be only about 8% of an inch of obstruction due to curvature, were the Earth a sphere with the given dimensions.
Again, fraction of an inch. You're not going to be able to see that over a mile using a camera in your eyes.
You'll notice as the video progresses that more and more of the pelican's body appears obstructed as the distances increase.
So they're suggesting that they're seeing more obstruction than the calculator would suggest. And in fact, if they had put refraction in there, the calculator would have put that number even lower. There would probably be 0 obstruction. You probably wouldn't miss anything due to refraction tending to raise the image in the distance. However, 1 mile, 1 inch, that's really not gonna cut it. I mean, that's not what the curve calculator is intended for. It's intended for long distance observations, and 1 mile is not a long distance observation. So I guess they're suggesting that they're seeing more obstruction, which you'll see in the upcoming images. And then the calculator would suggest, which I suppose they are implying that the calculator is wrong. I say that they're using it incorrectly for a start, not understanding how to use it or where it's applicable.
We started the observations at 1:15 p.m. The air temperature was 82 degrees, humidity was about 18%, and the water temperature was approximately 75 degrees.
So that's nice information to have. They also repeat that at the end and give the change that occurred over the course of time that they were there. A temperature of the water, an air temperature, and humidity. However, the air temperature they gave is just an air temperature. We don't know where that was taken. Was it taken 12 inches above the water? Was it taken 5 feet above the water? Refraction is due to gradients in air temperature, changes in air temperature, not just to a temperature. Having an air temperature does not give you the information you need to make any kind of determination on refraction. So why bother? I don't think they understand the causes of refraction if they're going to give insufficient information. I'll pause it here, and I'll just add one more point. That is that the video that goes on to just give us several minutes of pictures of mirages and mirroring effects and so forth. I'll come back to that in a moment. The rest of the video is basically just a lot of poorly focused shots of ducks and various other birds moving over the water. We're seeing various mirage effects mirroring. That at one point they pause it and give us a mirror line. We have, let's see, 255. Where's 255? Okay, we have, let's see if I can find a couple more things here. We've got some ducks going by where we only see the heads. Then Finally, at the very end, we get a little teaser.
We're looking forward to bringing our boats out to this.
For some reason, at this point, everything has come nicely into focus again. It would be really great if the rest of the images could be this focused. If you're going to do more of these videos, please do try to learn to use the equipment better. I'm sure there's things you can do to improve the quality of the images you're getting. Again, if you're expecting to get anything meaningful from this regarding the shape of the Earth, it's not going to happen. Over 1 mile on a lake, you're not going to see any kind of, you're not going to gather any kind of useful data regarding Earth's shape. So if that's what you're after, get up above the water level. Stand up. You don't need to put your camera in the water. It doesn't help. It just makes things worse. Stand up, get a good view of what you're looking at. Take some careful measurements. Get some surveying equipment if you can. Measure some angles. This isn't going anywhere. This line of observation here isn't going to go anywhere. Anyhow, I'm going to cover a whole lot of this in the next videos that I come out with. It's going to be a set. I don't think it'll all fit in one video, so I'm going to probably do 2 or 3. And it's going to be called a primer on long distance observations for globies and flatties alike. That's the working title. And it's going to raise the key points about what are you trying to accomplish with your observation. Is it in order to learn more about atmospheric effects, or is it in order to learn more about the shape of the Earth? And if so, you've got to understand how to use your tools, how to plan your observation, what information, what data is necessary to obtain in order to do some decent analysis, how to do the analysis. This is the stuff I'm going to cover, and I hope it'll be a kind of a generic response video that I can point people towards for all these long distance observations, because they all seem to fall down on the same 2 or 3 points. Anyhow, that's it. Enough. I'm going to start a ramble again if I don't stop. So wish you all a great day, and hit that like button, subscribe, share this with friends. Thanks. Bye-bye.